Hello and welcome to a lesson on the rules of indices. This lesson will be equally applicable to higher tier GCSE and to the early modules of A-level. What I'm going to do is deduce the 8 rules of indices by looking at examples in algebra. Then once I've got all the 8 rules of indices, we look at a further 10 examples to put them into practice. So let's begin. Let's first begin by considering y squared multiplied by y cubed. What does that actually mean? Well, y squared is y times y, and y cubed means y times y times y. So if we multiply those together, the brackets actually serve no useful purpose. We can just remove the brackets. So we've got y times y times y times y times y. But that is exactly what we mean by y to the power 5. So y squared multiplied by y cubed means y to the power 5. Now that leads us to our first rule, a more general rule. If we've got x to the power p multiplied by x to the power q, then what that's going to give us is x to the power p plus q. Because if we've got 2 lots of y multiplied together, and here we've got 3 lots of y multiplied together, altogether we end up with 2 plus 3 lots of y. So more generally, if we have p lots of x multiplied together, q lots of x multiplied together, then altogether we'll have p plus q lots of x multiplied together. Moving on now to find a second rule for indices. Let's consider y to the power 5 divided by y squared. What do we mean by that? Well, let me write out y to the 5 first. And then divide that by y squared, which is y times y. Now what I can do now is start cancelling the y's. I can cancel that y with that y, replace them with 2 1's. I can cancel that y with that y and replace those with 2 1's. But I've now run out of y's on the bottom to cancel, and what I've got on the top of the fraction, I've got y times y times y, which is y cubed, and on the bottom I've just got 1 times 1. So y cubed divided by 1 is just y cubed. So now look what's happened. Y to the 5 divided by y squared is y cubed. The 2 y's that ended up in the denominator, multiplied together, cancelled out 2 of the 5 I had on the top. And that leads me to my second general rule. If I've got x to the power p divided by x to the power q, I will end up with x to the power p minus q, because q lots of x will cancel out q lots of x on the top, and I'll be left with p minus q of them multiplied together. For our third rule of indices, let's begin by considering y squared all cubed. If we want something cubed, we want the thing multiplied by itself again. So this is equal to y squared multiplied by y squared multiplied by y squared. But it's important that our rules for indices are consistent. So this has to be consistent with our first rule. And our first rule tells us that y squared times y squared is y to the 2 plus 2, which is y to the power 4. Then when we multiply y to the power 4 by y squared, again by our first rule, we get y to the 4 plus 2, which is y to the 6. So for consistency, we require this answer to be y to the 6. And we can also verify that by writing everything out in full, because y squared is y multiplied by y. The second y squared is y multiplied by y. And the third y squared is y multiplied by y. And if I multiply those together, then what I've got is 6 lots of y all multiplied together, which again is precisely what we mean by y to the power 6. So that leads to our third rule, generalizing x to the power p all to the power q is equal to x to the p times q, which we can write as pq. Y squared all to the power 3 is y to the 2 times 3, y to the 6. But 2 and 3 could be any numbers, so x to the p all to the power q is x to the pq. And we now have the most 3 important rules of indices. The other 5 will all follow automatically from these 3. So let's find rule number 4. Let's consider y to the 4 divided by y cubed. Well, y to the 4 is y times y times y times y. And if I divide that by y cubed, we can see that I can cancel y with y. I can cancel y with y again. I can cancel y with y again. And all I'm left with is y on the top, times 1 times 1 times 1, which is still y. And on the bottom, 1 times 1 times 1 is 1. So the answer is y. So y to the power 4 divided by y cubed is y. But to be consistent with our second rule, we have y to the 4 divided by y to the 3 is y to the power 4 minus 3, to be consistent with our second rule. And 4 minus 3 is 1, so that has to be y to the 1. So we have to agree that what we mean by y to the 1 is just y itself. And that gives us our fourth rule. X to the power 1 simply means x itself. Moving on to deduce our fifth rule, let's consider y cubed divided by y cubed. Well, anything divided by itself is 1. But to be consistent with our second rule, y cubed divided by y cubed has to be equal to y to the 3 minus 3. But 3 minus 3 is 0, so that has to be y to the power 0. So for consistency, we need y to the power 0 to mean 1. And that gives us our fifth general rule. X to the power 0 always means 1. Let's move on now to obtain our sixth rule. Let's consider y to the power 3 divided by y to the power 5. I'll write it out in full to start with. Y times y times y on the top, and on the bottom 5 lots of y all multiplied together. And now we start cancelling. I can cancel y, and again, and again. But this time I've run out of y's on the top. So on the top I've got 1 times 1 times 1, which is 1. And on the bottom I've got y times 1 times 1 times 1. So the y times y gives me the y squared. Now, to be consistent with our second rule, y cubed divided by y to the power 5 must be y to the 3 minus 5, which in turn is y to the power minus 2. So we now need to recognize that when we see y to the power minus 2, it actually means 1 over y to the plus 2. And more generally still, if we've got x to the power minus p, it actually means 1 over x to the power plus p. So it's important to realise that negative powers of x do not mean negative numbers. There could be a negative sign at the front, but the negative sign in the power doesn't affect whether the number is positive or negative. X to the minus p is 1 over x to the p. To deduce our seventh rule of indices, we'll consider y to the power a half multiplied by y to the power a half. Now, to be consistent with our first rule, that has to be y to the half plus a half. But that means it's y to the 1. A half plus a half is 1. But we've already agreed that by y to the 1 we mean y. So we now have y to the half times y to the half equals y. But that's what we mean by the square root of y. So y to the power a half means the square root of y. And let's put a little 2 there to denote it is the square root. What if I consider y to the power 1/3 multiplied by y to the power 1/3 multiplied by y to the power 1/3? Well, again, by our first rule, y to the third times y to the third is y to the third plus a third, which is y to the 2/3. Y to the 2/3 times y to the third is y to the 2/3 plus another third, which is y to the 1. And again, we've agreed that that means y. So this is a number which multiplied by itself again, gives y. So y to the third is what we mean by the cubic root of y. The number which times by itself again, gives you y. And that gives us our seventh rule. X to the power 1 over p gives us the pth root of x. So x to the half is the square root of x, x to the third is the cubic root of x, x to the power a quarter would be the fourth root of x, and so on. So now just one more rule to deduce. Let's consider y to the power 2/3. We could think of that as y to the power 1/3 squared. From rule 3 we know that y to the third all to the power 2 is y to the third times 2, which is y to the 2/3. So that means I could find the cubic root of y and then square it. But an alternative way of looking at this is y to the power 2/3 is equal to y squared to the power 1/3. Because again, 2 times a third is 2/3. So we have a choice here. If we want to evaluate y to the 2/3, we can first find the cubic root and then square it, or we can square it and then find the cubic root. So in general, if I've got x to the power p divided by q, then that is equal to the qth root of x all to the power p, or alternatively, it can be the qth root of x to the power p. Now, in general, these questions crop up on exams when you haven't got a calculator, and if that's the case, it's easier to find the root first and then the power. That keeps the numbers much smaller. If you've got to find a power first, you can end up with a large number and you won't know the root of that particular number anyway. So we've now got our 8 rules. Let's have a look at a summary of them. Right, we'll now look at 10 examples that utilise each of these rules on the left-hand side of the page. Example 1. 2x squared multiplied by 3x cubed. It'll be helpful here on this first example to write this out in full. 2x squared means 2 times x squared multiplied by, and 3x cubed means 3 multiplied by x cubed. So here we see it's 2 multiplied by 3 is equal to 6. X squared times x cubed, using our rules of indices, is x to the 2 plus 3, which is x to the power 5. Now I've deliberately chosen this example to illustrate that the fact you've got a 2 here and a 3 here, and a 2 index and a 3 index, they don't end up the same in the answer. So you're treating the numbers the same as we always treat numbers when we multiply, and 2 times 3 is 6. But the indices, x squared times x cubed, is x to the 5. Example 2. 10x to the power 10 divided by 2x squared. Well, this can be written as 10x to the 10 over 2x squared. And here we see 10 divided by 2 is 5, but x to the 10 divided by x to the 2 is x to the 10 take away 2, which is x to the 8. So there's another illustration that even though we've got a 10 and a 2 numbers at the front and a 10 and a 2 for indices, they didn't end up the same in the answer. Moving on now to example 3. 2x squared all to the power 5. Again, I'll write it out in full. It will be 2x squared multiplied by 2x squared multiplied by 2x squared multiplied by 2x squared multiplied by 2x squared. I'm not suggesting you should set your answers out in this way, but just to illustrate what's going on, I think it's useful with our first examples. And here we can see there's a 2 times 2 times 2 times 2 times 2, which is 2 to the power 5. 2 to the power 5 is 32. But the x squared to the power 5 gives us x to the 2 times 5, which is x to the 10. So you need your wits about it to realise that when you've got something in a bracket to a power, what happens to the numbers at the front is not the same as what happens to the indices. Example 4 next. Seven to the power 1 is what? Well, x to the power 1 is just x, so 7 to the power 1 is just 7. Example 5. 8 to the power 0. X to the power 0 is 1, so 8 to the power 0 is 1. Example 6. 5 to the power minus 3. Now, whenever we have a negative power like this, the best thing to do is get rid of the negative power straight away. So instead of 5 to the minus 3, I'm going to write it as 1 over 5 to the plus 3. I won't actually write the plus sign, but 1 over 5 to the 3. And now I can concentrate on evaluating that denominator. 5 cubed is 5 times 5 times 5, which is 125. So the answer is 1/125th. Example 7. 8 to the power a third. 8 to the power a third means the cubic root of 8. Well, the cubic root of 8 is 2. 2 times 2 times 2 gives you 8. Example 8. 9 to the power 3 over 2. Well, 9 to the power 3 over 2, the easiest way to do it is to find the root first. So it's the square root, it's the bottom of the fraction that gives you the root, the square root of 9, and the top of the fraction gives you the power. So it's the square root of 9 cubed. Square root of 9 is 3, and 3 cubed, 3 times 3 times 3 is 27. Now contrast how easy that was to what it would have been if I'd approached it the other way. If I'd approached it from the point of view of saying 9 to the power 3 over 2 is equal to the square root, bottom gives you the root, of 9 cubed. Well, first of all, I'd have had to work out what 9 cubed is. 9 times 9 is 81. 81 times 9 is 729. And then I'd have wanted the square root of 729, which happens to be 27. But perhaps that's not common knowledge. So it's much easier to work out the root first and then the power. Example 9. 16 to the power minus 3/4. Well, as I said in a previous example, the best thing to do here is to get rid of the negative power straight away. So we can write this as 1 over 16 to the power plus 3/4. That's using x to the minus p is 1 over x to the p. Right, from there, we're working on the denominator, and we recognize that the bottom of the fractional power gives us the root, the top one gives us a power. So we want the 4th root of 16, and then we're going to raise that answer to the power 3, which is, well, the 4th root of 16 is 2. 2 times 2 times 2 times 2 gives you 16. So we want 1 over 2 cubed, and 2 cubed is 8, so our final answer is 1/8. And the last example, example 10. 10 p to the power 4 q squared r to the power 5 divided by 2p q to the power 8 r cubed. Right, treating the numbers as ordinary numbers, 10 divided by 2 is 5. P to the 4 divided by p is p to the 4 divided by p to the 1. P to the 4 minus 1 is p cubed. Q squared divided by q to the power 8 is q to the 2 minus 8, which is q to the minus 6. And r to the 5 divided by r cubed is r to the 5 minus 3, which is r squared. It's okay to leave the answer like that with the negative power, or alternatively, you could give the answer as 5p cubed r squared divided by q to the power 6, because of course q to the minus 6 is 1 over q to the 6. Either of these answers would do in an exam question. And that concludes this lesson on indices. Hopefully we've covered all the material you need to answer any question on GCSE higher tier or the early A-level module papers. You should now have a go at the associated exercise, which has 15 questions, very similar to the ones we've been doing, and the full answers are supplied.